Hello everyone, I am Ikram karabila from Sidi Mahmoud bin Abdullah University, Fez, Morocco. Thank you for having me at the International Conference on Intelligent Systems and Computer Vision. Today I am excited to introduce you a cutting-edge topic in the realm of recommendation systems. Our focus will be on a novel approach that leverages deep learning approach to revolutionize how we suggest content. Let's delve into the world of recommendation systems. During this presentation, we will follow a structured outline. Firstly, we will begin with a brief introduction to introduce the topic. Next, we will review the existing literature to provide context for our work. Following that, we will explain in detail the methodology we have employed. Then we will present our results and analyze them within the framework of an in-depth discussion. Finally, we will conclude our presentation by summarizing key points and highlighting the main conclusions. The exponential growth of data on the internet has led to a significant challenge for users who must navigate and select from an overwhelming number of options. To address this problem of information overload, recommendation systems have emerged as a solution. These systems help users by recommending items that are likely to align with their preferences and interests, thereby assisting users in making more informed choices amidst the vast sea of available information. While traditional recommendation systems have relied on collaborative filtering or content-based methods, their effectiveness is hindered by challenges such as sparse data and cost chart issues. To overcome these obstacles, it's imperative to incorporate additional information sources like user and item profiles. One promising approach is to merge the architectures of deep learning and ensemble methods, which can enhance recommendation systems by leveraging the intricate representations learned by deep learning models and the robustness provided by ensemble techniques. This integrated approach enables us to tackle the complexities of recommendation tasks more effectively, finally improving quality and relevance of recommendations provided to users. Some studies on recommendation systems are presented in our presentation. In the first study, the authors proposed merge CNN, a recommender system grounded in deep learning principles, employing both rating and review details for recommendations. The system adopts an attention mechanism coupled with CNN to extract user features from their reviews and latent vectors of items. The second study introduced a hybrid approach that combined a deep autoencoder with a one-dimensional convolutional neural network model. The objective was to enable a more precise acquisition of user and item features. Finally, in the third study, the authors introduced a deep collaborative recommendation algorithm addressing limitations in traditional collaborative filtering. This approach combines attention mechanisms to adaptively weigh user item representations, capturing implicit feedback's hidden information. The following table offers a clear comparison between previous studies and our proposed model in terms of techniques used. The majority of studies use matrix factorization in basic technique. For deep learning techniques, the first study uses attention mechanism and convolutional neural network for enhanced user feature extraction. The second study, introducing deep autoencoder with CNN for improved user and item feature acquisition from implicit feedback. The third study uses attention mechanism. Our proposed model stands out by integrating neural collaborative filtering and glove embedding with deep neural network for deeper contextual understanding and synergistic fusion with neural collaborative filtering model. This approach excels in enhancing recommendation accuracy by incorporating intricate patterns and contextual nuances in user preferences. As we can see in figure, the architecture of our proposal embodies a recommendation approach combining the neural collaborative filtering and glove with deep neural network techniques. This fusion is designed to enhance the reliability and effectiveness of user recommendations, effectively tackling challenges like sparsity and cold start issues with the recommender system. This integration offers solutions to handle scenarios with limited data and novel user item interactions more effectively. Having discussed the methodology, let's now transition to the presentation of our results. The source of the data used in our study is the guidebooks. To evaluate the proposed methodology, we conducted multiple trials comparing various approaches using a real-world dataset split into 80% for training and 20% for the test set. Two independent clusters were identified within these sets to analyze performance across diverse scenarios, notably focusing on user and item interactions. Categories such as all data and cold start were defined, with all data providing an overview of the dataset and cold start identifying limited or no existent interactions characteristic of the cold start scenario. This figure presents the results of neural collaborative filtering conducted on the dataset. This model yields metrics with an MAE of 0,87, RMSE of 1, 106, and MSE of 1, 22. This figure presents the results of glove embedding with deep neural network. This model demonstrates strong performance, achieving an MAE of 0,81, RMSE of 1,017, and MSE of 1,036. As we can see in this figure, the evaluation of the ensemble model that combines glove DNN with neural collaborative filtering showcases notably improved metrics. These results indicate a substantial enhancement in prediction accuracy compared to individual models. The ensemble's integration of various models effectively diminishes errors, leading to significantly enhanced accuracy. This figure presents the results of neural collaborative filtering when applied to the dataset representing cold start scenarios. The neural collaborative filtering model reports metrics with an MAE of 1,014, RMSE of 1, 24, and MSE of 1, 55. Conversely, the glove DNN model showcases strong performance with an MAE of 0, 87, RMSE of 1, 059, and MSE of 1, 12. As we can see in this figure, the proposed ensemble approach outperforms both individual models, glove DNN and neural collaborative filtering, in this cold start analysis, achieving an MAE of 0,70 and RMSE of 0,89 and MSE of 0,80. Consistent to the previous experiments, The ensemble model exhibits superiority over individual models in handling the cold start scenario. This further underscores its capability to leverage diverse models' strengths, resulting in a more robust prediction system. By combining various insights and leveraging diverse perspectives, the ensemble approach demonstrates superior overall performance. Notably, evidenced by significantly lower values across MAE, RMSE, and MSE methods. Table 2 and 3 presents a comparative analysis of performance metrics, especially mean absolute error and root mean square error for various recommendation techniques. The evaluation is conducted under two distinct scenarios, all data and data for cold starts. This comparative assessment provides insights into the effectiveness of the recommendation techniques across different data scenarios, shedding light on their performance in general and especially in scenarios with limited data. In Table 2, which corresponds to the all data scenario, various recommendation techniques were assessed using the complete dataset. The table showcases the MAO and RMS values for each technique, revealing notable insights into their predictive accuracy. Notably, remarkable is the ensemble model that combines neural collaborative filtering with glove DNN, which stands out with lowest MAO and RMSE values among all techniques. This result signifies superior predictive accuracy compared to individual methods. While neural collaborative filtering and glove DNN models also perform well, they exhibit slightly higher error metrics than the ensemble approach. Shifting focus to the data for cold start scenario in Table 3, where techniques are evaluated in situations with limited or non-existent interactions, the ensemble model once again emerges as the top performer. The ensemble model outperforms other methods, demonstrating its efficacy in handling cold start scenarios by providing more accurate recommendations in these challenging situations. These results underscore the efficacy of the ensemble approach in addressing recommendation challenges posed by limited or sparse data interaction. To conclude, in this study we proposed a novel recommendation system integrating deep learning and ensemble approaches. Our method combines neural collaborative filtering with the glove DNN model, using ensemble learning techniques. We conducted experiments on the good box datasets. The finding of the study demonstrates the efficacy of our proposed method. Finally, I would also like to share with you some of the bibliographical references that were essential for our study. Thank you for your attention.